Hello to everyone. So today I will present us three research things. One will be about a one-year-old research on Apple iPhone. Another is work in progress on Aud Smart Key, and the third one is the recent work I carried out on reverse engineering Insulin OmniPod. The Apple and OmniPod research are available as a paper, so you can see all the details online, and the slides are also available online. So first I will do a quick introduction. So I'm in the hardware security area for quite a long time. Started looking at Motorola microcontrollers used in cars. So I do a lot of testing of microcontrollers and smart cards for security. And I've graduated the PhD from Cambridge back in 2005. Did research on semi-invasive attacks. And then other noted achievements were finding backdoors in FPGAs, and one of the most attractive research was on iPhone 5C. And also I'll look at impossible solutions for hard problems in hardware security. So hardware security is about finding and fixing flaws. So you aiming at finding vulnerabilities and preventing attacks. And there are lots of challenges in hardware security, such as how well the data keys and passwords are stored. You have to be aware of new attack technologies, and the modern devices you are facing quite challenging fabrication processes, starting from 10 nanometers, while most devices will still be at the far end of about 65 nanometers, and even 65 nanometers, although it looks quite sophisticated, you can still see lots of structures under optical microscope. And also hardware security is aiming at developing countermeasures, and ideally you would like to be able to predict new attack technologies. So the important questions in any security research is how to find the best topic for the research. And usually those topics come from real life. You just look around and you see what's going on. So for example, how it unfolded with iPhone 5C, as if you remember, FBI wanted to recover information from iPhone used by one of terrorists, and they tried to get the information themselves, and at some point they announced that they cannot get any further without help from Apple. But unfortunately, Apple didn't want to cooperate, because FBI wanted them to update their operating system so that they can try as many passcodes as possible. And in iPhone 5C, it is the operating system that prevents you from entering more than 10 attempts. And then they went with a legal fight with Apple, and at one point at the press conference, the FBI director said that they tried all possible ways to extract the information, and the only way is to go through the software. And when he was asked whether the particular process of NAND mirroring would work, he replied that it doesn't work, and it's impossible to try more attempts with NAND mirroring. So that's the point when we were interested to see whether this claim was true or not. So the challenge was to look at the problem, look at the real device, and ideally make something impossible to prove them wrong. The next challenge came from my own experience when I bought a second-hand car from Audi dealership. I was given only 2 keys, while at Audi make a very strong claim to for the used cars is they pass a very strict 145-point checking process to make sure that everything was correct. And one of the part of this process is to check whether all the ignition keys in the vehicle are present, and that was obviously ticked. And then I accidentally found in the car menu that the number of initialized keys is actually 3. So I came back to them and asked what's the why the number of program keys does not correspond to the number of keys I was given, and I was told quite a strange response. Actually, that was by email, that that spare third key is a valid key, and if this key you are unable to start the car, you can only open the door, which sounded quite strange to me, because why would you code the third key if it's just a piece of plastic? And also they after some exchange of emails, they suggested that this third key, they can produce a new one and they can code it into the car. So that really puzzled me, that if it's a piece of plastic, how can you code into the car? So obvious challenge is to look into the user manual, because people don't look into the user manual, and it actually shows that the car should come with 2 normal keys, which is a radio control key and the third spare key, and the manual says that this spare key can actually be used to start the engine. So I decided to, just for curiosity, to look inside and to see what is inside the car key and how secure it is. And the third research came from a group of people that contacted me to help them, because they tried to build an artificial pancreas to help people with type 1 diabetes. So at the moment, there is no industrial solution for fully automated system that would control the blood sugar and at the same time deliver the required amount of insulin. So they already had a solution for the old tubed pump, but the pumps, the insulin pumps, the tubes are not that user-friendly, because you have tubes that can trick that are hanging around, and they can be tripped by furniture or clothes. So they wanted to use for their project a wireless tubeless pump, and the only wireless tubeless pump which is approved by FDA, because most of those people are in the United States, is the Insulet OmniPod. So they wanted to figure out how to communicate with this pod, because it comes with the controller, and this is what the pump looks like, and the controller is built with specialized hardware, and the communication is linked, and there's no documentation on how these devices are built and how they talk to each other. And the community involves the Loop project, OpenAPS, and the NiceCount Foundation, and they have a few hundred people working on a solution for this problem. But they came across the particular task of extracting the firmware from the insulin pump and analyzing it to find out how to communicate with it. So the obvious challenge was to help those people and to find out what is inside those devices and whether it's possible to extract the firmware. So what's common between all those projects is that usually the manufacturers make quite a strong security claims that these are unbreakable devices, that the communication is encrypted and secure. And obvious challenges from my side was to verify all these claims and to find the possible ways for improvement. And if I'm successful, then that would expose vulnerabilities, help to improve the design, and also attract attention to fund the existing projects and also continue the research and collaboration with new projects. So we'll start with iPhone 5C. So when FBI claimed that it's not possible to find other solution than changing the operating system, one of the experts in that area suggested that the NAND mirroring should work. He even came up with the software demonstration of this NAND mirroring, but because he used a jailbroken phone, which cannot be done to the victim's phone, then FBI said that it's not the really working solution, and the only way is to use the software approach. So what's the main problem with iPhone, and why you cannot easily guess the passcode is because after a certain number of attempts, you have to wait more and more for the next try for the PIN code. And after 10 attempts, the phone will be permanently locked. So you need a solution to be able to enter few attempts, then somehow restore the phone to the original state and then try it again. And also the security of the passcode verification is inside the hardware, inside the main CPU. When they ship the phone from the factory, they program so-called UID key inside the device, and then they use a hardware logic to calculate the actual key from the passcode user enters into the system. So in order to figure out what the actual decryption key is, you need to know both the UID key and the algorithm, how the decryption key is calculated. So that means you can either go the hardware way and reverse engineer the silicon, or you have to find a way to enter in as many passcodes as you want. And usually the passcode is only 4 digits, so you only need 10,000 attempts. So inside the iPhone there's a main board, and it's pretty straightforward to open it up and find the location for the CPU and for the flash memory. First we try to look at the CPU. So it's a relatively old A6 CPU in BGA package, and it also consists of two parts, the actual CPU and the DDR3 memory. And the CPU can be deprocessed so that you can see the internal structure of transistors and connections inside. But the main problem is that this CPU is built with the 32 nanometer process, and it would take enormous time and efforts to reverse engineer it and find out the key derivation algorithm and the locations for UID key. So even if you use the best optical microscope with 160x magnification and immersion lenses, you would still not be able to see much inside the chip. So you have to go with electron microscopy and make tens or even hundreds of thousands pictures. And so, and also because you don't know where this UID key is programmed, and very likely they use eFuse, but you don't know whether it's implemented as a polysilicon fuse, whether it's in metal 1 or metal 2, or even in the wires in between. So we'll have to deprocess the chip to various levels, try to find out the differences in fuses and transistors, and then do a very long reverse engineering. So obviously the only practical way would be to use non-invasive attacks. And Another possibility would be to find some kind of a backdoor, if Apple have it, for leaking those keys through, for example, side channel attacks, and also try to find the programming interface, because when they got the iPhone, they actually programmed those UID keys inside. So it might be possible to find the same interface and figure out how the key was programmed and probably read it out. But Apple claims that they shut down this interface once they programmed the key. So therefore we decided to try just the NAND mirroring process. So read out the contents of the whole flash memory, make a backup, and then run the phone for a certain number of passcode attempts, and then restore the contents of the memory. The first difficulty that I came across was that the NAND flash was not only soldered to the PCB, but also glued, and the distance between the NAND flash and the PCB is only 50 micrometers, so they placed very close to each other. But it was possible to just increase the temperature of the heat gun and carefully detach the flash from the PCB. So this is how it looks like, and after desoldering the flash, I then rewired it back to make sure that everything works just a normal phone. And then I made a card in the iPhone case so that I can use it in a normal way. But here came the first problem. When I started the iPhone, I saw the logger and then it crashed. And then also I tried to use iTunes to restore it, and it came with the verification error. So the problem was that those thin wires were not able to carry quite a high current, because at peak time it requires up to 2 amps. But because during the boot process the NAND was corrupted, the iPhone and the OS was does not restore it back to the original state. So I had to also wire reset, and the wire that forces the CPU to the recovery mode outside, and then force the CPU in hardware to go into the restore state and bring back the iPhone to the original operation. Then I replaced all the wires with sockets so that it would be easier to swap the NAND flashes, and also I built the intermediate board to eavesdrop on the communication with logic analyzer. And then I found that this intermediate board, because it inserted some delays in the data lines of the flash, again the phone stopped booting again. So I had to solve this problem, and this time it was much harder to solve it, because not only the data in NAND flash were corrupted, but also the iBoot that boots the whole operating system was corrupted. And whenever I tried iTunes to restore the phone, it came with the error message, and I was unable to find any tools that would restore it to the original state. So it's some kind of a catch-22 problem, because the phone, the iTunes trusts iBoot, and it also verifies it. But when iBoot works, it trusts the update server, and if you somehow corrupted the data inside the update server, just some files, then it just runs it, and because of the corruption, the phone crashes. So what I had to do is I deliberately inserted some delays into the data lines during the boot process, so that the iBoot was corrupted as well. And when you corrupt the iBoot, then iTunes verifies that it's corrupted and then restores both the iBoot and the update server, just everything. So once I got iPhone back to the operation, I hooked the logic analyzer and I figured out what communication protocol they use, because the NAND chips they use inside iPhone are non-standard NAND chips. They don't comply with the standard specification for NAND chips, and they use the proprietary commands. So you have to figure out all the commands and how to write, erase, and read the flash. And also those NAND chips, they programmed with unique serial numbers, so you cannot easily use NAND chips from another phone, because when you try to restore the operating system, you will get the activation error message. So you have to copy not only the data on the NAND flash, but also some configuration area that contains the serial number, so that the NAND flash will look exactly the same as the original. Then I built my own programming interface to test the communication protocol. I figured out how the NAND flash is programmed and accessed. So it has 4 megabyte blocks divided in pages, and each page is about 16 kilobytes with some indexing information. And then I built the board that uses another NAND flash to copy the original image, and then you can compare contents of both flashes and restore it. And then I wrote a simple software that was copying the NAND flash and then comparing two copies to see any changes during the iPhone operation, and then restored the contents of the original NAND flash. So then I ran the tests with the real iPhone, entered 5 or 6 passcodes until the delay is introduced, and then I scanned the NAND chip for any changes, and after that I erased the used blocks and wrote the contents of the original pages back into the NAND flash, and I was successful in the NAND mirroring. So after restoring the NAND flash, the iPhone was able to accept another 5-6 attempts and so on. And the video of the whole process is available on YouTube. There are certain limitations to this approach, that it only works for iPhone 5C, and the process can be fully automated to speed it up, and also the communication speed of the microcontroller was relatively slow, so you have to use some hardware solutions based on FPGAs to make it faster. And another problem is in the NAND storage cannot handle many thousands of rewrites, so you ideally would like to use some kind of emulators on FPGAs to emulate the NAND protocol and then restore its contents. And with other iPhones, only iPhone 5S and 6 use the same type of NAND flash. In iPhone 6s, 7 and later models, they use a high-speed NAND flash with PCI Express interface, so they will be much harder to copy and to restore. So the next work in progress that I'd like to present is the Aud Smart Key. So it's based on a relatively old Philips transponder IC that was designed in early 2000. And it's still used in the latest models of cars, which is quite surprising because the security they implemented 20 years ago is far from what modern attackers would use. And the same chip is used by other car manufacturers, and there are several similar chips in line. They've different memory size and features. And for those chips, you cannot find the full data sheet because only restricted information is available online. And by default, those chips use also very old high-tech 2 protocol, which was proved to be easy to break 5 years ago by the Flavia Garcia team. So they found that they use a 48-bit key inside those protocols, which is easy to guess by simply listening to the communication protocol and then brute forcing all the possible combination. And inside those PCF chips, they use the CPU, the RISC MRK2 CPU, and also on this CPU there's no information available. So the challenge is to look inside those devices and to see what hardware solutions they have. So those keys you can easily buy on eBay, and you can open it and look inside. They all have the same chip, also in different packages. So you can see that the original package have the antenna incorporated inside. It's quite thick, but if you buy the key from China, you will get a cloned key with the same chip in a thin package and the antenna next to it, but they all work the same. And the key in question was the plastic spare key, so I also bought them on eBay and I looked inside, and it's not just the plastic. So inside there's a small leadless IC, and if you decapsulate this IC, this package, you will see exactly the same silicon die inside as in the normal key. So it has absolutely the same functionality. The only difference is obviously you don't have the battery, so you won't be able to remotely open the car, but you will still be able to start the engine. Surprisingly, the chip has a different marking on the silicon die. So if on the package it says PCF 7945, on the die it says 7953. It has mask ROM, EEPROM, and what manufacturer called EROM, but it has the same structure as EEPROM, and SRAM and CPU. And it's fabricated with quite old 0.35 micrometer process, the 3 metal layers. So it's well outdated. And you can buy those chips on eBay and AliExpress, and also from various distributors, so getting samples is not a problem. You can even buy the programmers for these chips from eBay and AliExpress. You can buy the programmer for transponders, and you can buy a programmer for those normal ICs, so you can program any test data inside and see how the chip functions. I looked at different chips in the family. They have a very similar structure and just different packages, different memory size, slightly different layout, but the fabrication process is similar. Also, if you go to the chip manufacturer, you will see that they no longer offer those chips for design. They have much newer chips. I think they passed probably 2 generations of those chips, but for some reason car manufacturers are still sticking to the old 20-year-old design, probably for compatibility reasons. So the next step is to look whether you can extract any contents from the EEPROM, because it is the EEPROM inside those chips that holds the key. And I tried various non-invasive and semi-invasive methods, and I wasn't successful. And this is because inside EEPROM, next to the security fuses or security cells, they have some configuration cells, and if you disturb the contents of those configuration cells, then the chip doesn't operate anymore, so you can easily destroy the chip by trying various non-invasive and semi-invasive attacks. So I went for invasive methods, and if you can use microprobing, but that would require FIB editing, which is not easy to use, but possible. You can try to use scanning probe microscopies, but that required quite sophisticated sample preparation. So I went for a scanning electron microscopy to see whether I can see any data inside the chip. And for 0.35 micron electron microscopy works pretty well. Although the contrast is not superb on the chip, you can still see the differences between the programmed and non-programmed cells. So you would have to apply some sort of signal processing and image processing to restore the data. But the good thing is you can get as many samples as you like, and you can test those samples and figure out the layout of the internal memory. So I analyzed the similar chip from the same family, 7941. So I imaged the memory. I tried to figure out how they distribute the data and addresses inside. So the addresses are just sequential, and they don't even use any encryption for the memory or XORing. They just use a permutation table for all the data lines. So they instead of having sequential D0, 1, 2, 3, 4, and so on, they just swapped the data lines, which makes analysis much easier. So you don't have to find the decryption key, or you don't have to find the tables for each memory location. And inside the memory, you have for high-tech protocol, you have either 48 or 96 bits of the key, and if you use AES key, then you have 128 bit. The only advantage in security of those chips is because they have a CPU inside and a user memory, so the manufacturer can easily upgrade the security of the car key by programming their own algorithm rather than using old and outdated high-tech. So that way they can improve the security of the key. To summarize on this project, so the attack works for old EEPROM technology because the chip uses 0.35 micron. It wasn't that difficult to extract the memory. And in order to have a proper protection, you have to use memory encryption. And also what makes difficult in attacking those chips is the lack of any documentation. Obviously I proved the audit leadership wrong by their claim that the plastic spare key is just a piece of plastic, so it can be actually used to start the engine and to drive the car. And it has exactly the same functionality, exactly the same chip inside as the standard key. What I didn't know is what exact protocol they use in those keys, because it might be high-tech, it might be AES, or it might be a proprietary protocol, and the sensitive information can still be extracted, but if you don't know what protocol they use, then you obviously won't be able to use the data. So the last project I would like to present is the reverse engineering of Insulet OmniPod. So the project was to help the community of people with type 1 diabetes, and the original setup, as I already mentioned, consists of the PDM controller and the insulin pump, and they use custom hardware without any information available. So the first step was to open up the port to see what is inside, and that can be achieved with relatively simple engraving tools with the circular saw attached to it. So you just cut the plastic around, and the video of the process is available on YouTube. So inside the port they have quite interesting mechanical solutions, because they have motor, which is not driven by the electric field, but it is driven by muscle wires. The muscle wires is a special type of metal wire that when it's heated, it doesn't expand, it actually contracts. So it pulls the lever, the anchor inside the device, and that way they turn the gears, and those gears are connected to the mechanism that inserts the cannula inside the skin. So they have a pretty strong spring that pushes forward the needle with the cannula, and then after insertion into the skin, the needle is retracted back. And also they have the mechanism that allows you to fill the tank with the insulin, and then they have some kind of the clutch spring that locks the rod inside this construction, so that with turning of the gears, then the insulin is pushed outside of the tank into the body. So they have a PCB attached to the construction, and as you can see on the PCB, they have just one integrated circuit with a few components around. So the first thing I did is I traced all the connections between the integrated circuit and the mechanical part, and they only have two-layer PCB, so it was relatively easy to remove all the components and trace all the connections, and then you can create the schematic. The next step was to identify the IC they use. So the marking did not show anything standard, so it looked like the 8-bit Freescale microcontroller, but without any readily available documentation. So then the next step is to try to figure out the connections of the pins, and also I analyzed the wireless communication, and the most part of this analysis was already carried out by the OpenOmi community. They found that the communication is at 433.9 megahertz with FSK2 modulation, and with 4625 baud rate with some error correction. So then I traced the connections from the silicon die to the outside package, and the chip has a very similar marking what is used for HCS08 microcontrollers, and in fact the chip is based on the standard microcontroller Key32 with addition of special functions, for example the voltage regulator, the buzzer controller. They have a couple of power MOSFETs to drive the engine, and they have added the RF communication module. But obviously the pinout and the allocation of the CPU registers is different. So the next I looked inside the chip to see what is on the silicon die, and the silicon die marking tells exactly the same as on the package. So it's ER48 microcontroller, and I traced the connections of the bonding wires, and I confirmed the fabrication process is 0.25 micrometer, which is not very advanced. They've 5 metal layers, and it has 48 kilobyte of flash memory on the chip and 4 kilobyte of SRAM. And I also found other sources of information about this chip, because for some reason, for example, Google was able to index some hidden NXP website pages that contained information about the fabrication process on this chip, that also that didn't show more than the 0.25 micron process used, and the memory size, and what material they use for bonding wires and for the package. And next I looked at the development tools which I used for HCS08 family of microcontrollers, And surprisingly, inside those tools, there's information about this particular chip used in the insulin pump, and that came with the pinout and the description of the CPU functions and addresses for all the CPU registers. And also, I found that some universal programmers, for example, LNAC-bproc, supports this chip, and also the pmicro flash programmer, which is part of the development tools used, is also support this chip. So you can easily program the chip, provided you know the pins to connect the debug interface. But it was relatively easy to find the location of the pins for debug interface, because you only need 2 pins. You don't need reset and BKGD pin, and those can be easily figured out by looking at the voltages during the device operation. You can trace them from the silicon die, or you can use an adapter with the universal programmer, or you can learn them from the development tools. So that allowed me to draw the circuit diagram of the insulin pump. You see, it's very simple. The most components are just bypassing capacitors, and the pins are directly connected to the mechanical part of the device. And next, I tried to access the firmware by hooking the ports to the development tools, and then it wasn't surprising that the tool came up with the message that the device is secured. That was well expected, and the only option you have is to mass erase the flash, and only after that you can reprogram it. So the next step was to find some way to extract the firmware from the chip to access the memory. I tried various non-invasive and semi-invasive attacks, and that was unsuccessful, because they did implement, actually, also it's a standard microcontroller, Freescale implemented some countermeasures against known attacks. And therefore I went for invasive attacks. One option was to use FIB editing, and that wasn't successful. And then scanning probe microscopy is not easy to use, and it's very time consuming, so I went for electron microscopy with passive voltage contrast, and that method works down to about 180 nanometers, but the chip was 250 nanometers, so it worked relatively well. So you can see the difference between zeros and ones. Also, it's not very good contrast. You can see some, so this area is all ones, and you can see that some bits are programmed, so you can see the difference in the intensity. And then I wrote a MATLAB code to check the and convert the image into the hex file for disassembling, and also applied some image processing, which is also available as part of MATLAB tools. And then after the image analysis, you draw the histogram, and you can see how well the zeros and ones are separated. So ideally, you need them to be quite apart, so you can detect zeros and ones with high probability. And because that wasn't the case, as you can see, the image doesn't have very good contrast. I had to process several samples and then combine them together to produce the final hex file. And then once the file is produced, then I can use the disassembler to produce the assembler code, and for that I used Hexray IDE Pro, because it supports this family of microcontrollers. And also, ideally, you would need to create a configuration file for the disassembler, because otherwise, instead of meaningful CPU registers, it will just give you the address. So you have to create the file, and all the necessary information for creating this file for special CPU registers was available from the development tools. And then finally I tested the hardware. So I programmed the used port with the hex file I extracted, and it worked just like a new port, except for the mechanical part, because once you activated the cannula insertion mechanism, once you locked the tank membrane mechanism, you cannot refill the tank or insert the cannula, and the whole process is available on YouTube. And once you got the working hex file, you can use various debugging tools to test how the device operates. You can reverse engineer the firmware, but that will be carried out by the people already building the artificial pancreas. So it will be their job to analyze the code and to use that information to build their own device, because initially they used the simple computer for controlling the port, and ideally they want to use smartphone to connect the glucose monitor with the port. And also I also looked at the flash memory contents after the device operation to see what changes are made to the flash memory. And there are certain limitations for the memory extraction process I used. So the electron microscopy works down to about 181 micrometers and for the EEPROM, and only 250 micrometers for flash memory. And the reason for that is because the old process, something like 0.35 micron, you have about 50,000 electrons on the floating gate. But if you look at the modern flash process, for example, 16 nanometers, you will end up with less than 50 electrons on the floating gate in some cases. And when you put the device under electron microscope, you need a relatively large number of secondary electrons to hit the detectors to see the differences. And also the thickness of the dielectric between the gate that stores the charge and the outside environment is usually less than 4 nanometers. So that means the electrons can easily escape from the floating gate. And remember that under electron microscope, you have relatively high beam energy. It's in excess of 500 electron volts. So those electrons can, if they hit the electrons on the floating gate, then they make them escape relatively quickly. And also, if you look into large memory sizes in modern devices, that it will be much more difficult compared to just kilobytes used in old devices. So that means more efficient methods and solutions are necessary if you want to use electron microscopy for memory extraction. And obviously because the memory wasn't encrypted inside those devices, I was able to easily extract the firmware. But if they used memory encryption, that would be far more difficult, because I would have to find the keys and decryption algorithm. And what made it harder is the lack of documentation. But I was able to find at least some information in the public domain. If there was no information like the smart cards, that would be absolutely a different story. So about the future work and collaboration, so I'd like to be involved more the failure analysis methods, because the modern devices, you can no longer use low cost and easy non-invasive and semi-invasive methods. You have to go for invasive methods, and the best invasive solutions, they come from methods and techniques used in failure analysis. And also I would like to improve the existing methods used in scanning probe microscopy and electron microscopy. And that means the closer collaboration is needed between the industry and academia, because in academia you come up with some non-standard and even crazy ideas, but you need the ability and of industry to try those ideas and to implement them. And for any research in that area, funding is essential. So you always need a good collaborator to try and implement the ideas. And so the main direction of my current research is aimed at direct imaging of the embedded memory. So I would like to use combined methods, not just using the existing equipment, but try to come up with a new solution and new approaches. And that means more research is needed. And I have a dedicated page on this project, but at the moment there's not much available except for the results for electron microscopy. So to conclude, there's always interesting target for security analysis and security research around. You just have to pick up the most interesting one. And it's not always true that the newest devices have the best security features. You can still find that modern devices do not have very strong security protection. And it's not always true what big companies or government tells you. So sometimes they lie about the security, and also when it comes to the money. Ideally, you should be able to verify all the strong claims, and even if you come across something impossible, there could be a way around it. So my message is to be creative and be innovative. And thank you for your attention. I hope you enjoyed it.